So welcome everyone to this RISE seminar today. So we have the pleasure of welcoming Vijay Chidambaram from UT Austin. So he is an assistant professor that works at the intersection of systems and storage. Um, his work is pretty broad. He works from machine learning, storage for machine learning, crash consistency for file systems, and the interaction between storage and the law. So he has many, many awards and many, many SOSP OSDI publications. The one that I remember off the top of my head is that his dissertation won the Dennis Ritchie Dissertation Award. So we're very happy to have him, and we very much, or at least I very much look forward to his talk.
Thank you, Natasha. So hi, folks. So I'm going to be talking to you about building storage systems for new applications and new hardware. And feel free to interrupt me at any time and ask questions. The talk has like Slack built in, so we can handle questions at any time. All right. So anything that we do today, right? Watching movies on Netflix, to playing games on a mobile, to running sort of like traditional databases or key value store, all of it sort of like requires storage. Storage is sort of like one of the fundamental bedrocks on which all of these services are built. Storage, the designers of storage services have always had challenges, but these days they face like new and interesting challenges. One of them is new hardware. So Intel recently released this new hardware called persistent memory, which is a storage class technology. I'll be talking more about it in a bit, but that's come along and that's made things very interesting. In like 5-10 years down the line, we will have the ability to write our data into DNA. So like imagine writing your data into like a strand of hair, or like writing your data into like a piece of glass. So Project Silica is something that does that. And so we have all these sort of new hardwares coming out and like sort of like on the horizon, and it's made things very interesting. Another thing that's happening is we have new applications which put new stresses on top of the storage system. So for example, everyone talks about machine learning, but there's also things like blockchains and new privacy regulations such as GDPR and CCPA from California, which put new stresses on the storage system. And we'll talk about like how we handle that. We are also sort of like more concerned with old metrics such as like device lifetime. So in our quest for performance, we don't want to burn through like a million SSDs. We want to make sure that we use our SSDs as much as possible and we get the most performance we can while the device is still alive. So that's another thing that storage designers have to take into consideration. So over the years, my group, the UT Systems and Storage Lab, has tackled these challenges. And when I started at UT, like I sort of like continued my bread and butter work from Wisconsin, where I did my PhD, where I worked on how do you build reliable storage systems. So I worked on that on like a single node and then across a distributed system. But then we sort of like branched out. So we worked on how do you build a write optimized storage, which gains the same performance as like regular systems, but writes much lower amounts of data to storage. How do you build storage for persistent memory, the new device that's come out from Intel? How do you build storage for machine learning? And how do you build storage for new regulations like GDPR and CCPA? So all of the work here is sort of like done by my amazing students. I'm just like highlighting them. I'm happy to talk about any of them sort of like offline. In today's talk, I'm going to talk in detail about 3 words and sort of like briefly mention a few others. Okay. So first, I'm going to talk about new storage technologies, specifically persistent memory. So Intel announced this technology in April 2018, and this is a storage class technology. So if you write data to it, you lose power. When you come back up, the data is still there. It's durable, but it's connected directly to the memory bus. So you access it the same way you would access DRAM using processor loads and stores and so on. Right. So compared to DRAM, it has like slightly higher read latency, lower read bandwidth, and significantly lower write bandwidth. So compared to DRAM, it's sort of like a more bandwidth constrained device. But compared to solid state drive, which is the previous fastest durable media we had, it's about orders of magnitude faster. So it's quite a big leap in terms of like the system, the media on which you can build storage systems. People have been working on the question of like, how do you build storage systems for persistent memory for a really long time? It's like the earliest references go back to actually like 1960. But even in more recent times, people have been working on data structures for persistent memory and file systems for persistent memory. So the first part of my talk, I'm going to talk about file systems for persistent memory. And what we're going to do is we're going to take open source persistent memory file systems, and we're going to measure the performance for a simple operation, appending 4 kilobytes of data. Okay. So here in this particular slide, in this graph, we have the x-axis is the raw persistent memory device and the various open source persistent memory file systems. And y-axis is time taken to do the operation in nanoseconds. So first, we notice that in the left part of the graph, we have the time taken to write 4 kilobytes to the device. So this is without a file system, just like you open up the device and you write to it. And this takes about 700 nanoseconds. So unless you're using deduplication or compression, this is going to be the minimum time taken to sort of like write data to the device. So this is going to be our baseline. On the right hand side, you see the time taken to write, write 4 kilobytes of data through the ext4 file system. This is a mainline file system in the Linux kernel, and there's a mode that is used for persistent memory, and sort of widely used. And we see that it takes 9,000 nanoseconds, about 12 times more time than sort of like writing 4 kilobytes down to the device. So we call this gap the software overhead, right? The difference between what the device can give you and how much time it takes where you do the system. Right? And we want to reduce this software overhead. And various research file systems have done this. So PMFS, No and Starter have reduced the software overhead quite a bit. You still see that the overhead is about 2,500 nanoseconds, right? So we have like about 2.5 times overhead. The question is, can we reduce this even further, right? And that's what we try to do in this project. And the way we do this is by taking a really old idea and by putting like a new spin on it. Okay, so the idea is simply this. Whenever we have data operations, such as like reads, in-place writes, and so on, we are not going to trap into the kernel to do it. We're going to do it directly from user space using processor loads and store instructions. No kernel involved. Whenever we want to do a metadata operation, such as creating a file, renaming a file, and so on, we are actually going to trap into the kernel, and we're going to use an existing kernel file system, such as ext4, to do these operations. Okay. So why did we sort of like arrive at this design? We built this file system based on this called SplitFS, and it's a collaboration with Georgia Tech and Penn State. And the intuition is that when you're looking at file system operations, right? Data operations are relatively simple. So if you want to code up like the data path yourself for like a read or an in-place write, you can do that and fairly expect that you would have done it correctly. However, for metadata operations, such as like file create, rename, and so on, these are very tricky. And previous research has shown that when people try to implement POSIX, all of the corner case of POSIX correctly, they inevitably make mistakes. So implementing metadata operations is a very complex thing, and it's not something that you want to do. So this is why we partition our design in this way. And if you look at the spectrum of designs for file systems, right? So on one hand, you have persistent memory file systems where all operations go into the kernel. So if you do a read, if you do a write, everything goes into the kernel. And ext4, PMFS, and Nova are built in this approach. And this gives you low complexity because you're able to take advantage of a lot of the scaffolding that is inside the kernel. For example, the virtual file system layer. You can use that to build your file system. So it reduces the complexity of what you have to write. But it also provides low performance, right? Because for every operation you're trapping into the kernel, and the latency for for read or write on persistent memory is only about 100 nanoseconds. So every trap that you're making to the kernel is very expensive. On the other end of the spectrum, we have file systems like Strata, which are entirely in user space, right? It seems to make sense. And they give very high performance, like you don't have to trap ever into the kernel, so like you're doing everything from user space. The problem though is that you have to end up implementing a lot of the functionality that was previously in the VFS in your user space code. So this makes your code kind of hard to maintain because like you have to make sure that you get all the metadata cases correctly, you have to make sure that all the bug fixes are done and so on. So it makes it hard to maintain. There are other intermediate points, such as like ARI from Wisconsin in Eurosys 14, where they basically said, we're going to have kernel interactions, but we're going to minimize them. So if, for example, let's say you want to allocate a block, when you go down to the kernel, instead of giving you a block, they will give you an entire big extent, give this to user space and say, hey, do whatever you want with it. And so this reduces kernel interactions. But ARI was really built for a different use case, where every application gets a different interface, not POSIX. And this shows in its performance. So ARI is about 30% slower than ext4 DAX, whereas we want to be faster. So this brings us to SplitFS, where we're going to handle data operations in user space and metadata operations via an existing file system. Okay. And we argue that this is the right design because it gives you high performance. Because in a data intensive application, most of your operations are going to be data operations, not metadata operations. So you're going to be accelerating those. And you get low complexity because you don't have to handle any of the metadata operations yourself. You're going to route them through ext4. So we argue that this is the right way to build persistent memory file systems. And the bet that we're really making here is that we are willing to take a hit on metadata operations. Because we don't re-implement them ourselves, because we use the ext4, those are going to be slower than, let's say, in a research file system like Nova or Strata. However, we are going to accelerate your data operations. And the bet is that we get so much performance gain from the data operations that we can absorb the hit we take on the metadata operations. So that's the high level bet that we're making. Did we have a question? Okay, so I'm going to go ahead. So this is the architecture of SplitFS, and we have an application which is a process, and we have two components, hence the name SplitFS. So in user space, we have our innovatively named uSplit, which is our user space component, and inside the kernel we have ksplit, which is simply like ext4 tags. Whenever the application does a read or a write, we're going to do LD preload, and we're going to capture all of those calls, and we're going to route them through our library. And for read and in place writes, we are not going to go to the kernel. We're going to go down directly to persistent memory. Okay, so no kernel involved there. However, when the application does metadata system calls, just like create and delete, we're going to go down into the kernel and we're going to just route it through ext4. So this gives us two advantages. One, as I mentioned before, we don't have to implement all these corner cases, saves us a bunch of time and effort. The other is that it gives us security, because every time you open a file or you create a file, you have to go through the kernel, and the kernel is going to do the same checks that an in-kernel file system would do. You're going to check whether you have the right access permissions to do this and so on, right? So we get all those security checks because we're going through the kernel. We also have a log that is associated with each user space component, and this log can be used to provide properties such as atomicity. So if you want properties such as like all my writes are going to be atomic, irrespective of the size, we can do that because we have this user space log. So another interesting feature that SplitFS provides is that we can have different applications can get different guarantees from the same file system. So if you take an internal file system, let's say ext4, and you're running it on Linux, you have a partition and you mount your file system on top of that partition, and you set properties such as like data journaling or write back journaling and whatever. And all applications writing to that partition will receive the same guarantee, right? So different applications cannot get different guarantees. But you can do this with SplitFS. So we have three modes, which we call like POSIX, sync, and strict. And one application can say like I want strict guarantees, like I'm willing to take the performance overhead associated with that. So one application can do that. Another application can say I am actually doing a lot of stuff myself. For example, SQLite does this, and so I don't need any reliability guarantees from the file system. I'm going to take care of it myself. Give me just like the raw file system, and we can support that as well. And these two applications can run side by side on the same partition. This is not something you can do with the in-kernel file system. That's a very interesting feature of SplitFS. So in summary,
I have a question for
hey,
you.
we had a question.
Yeah, I want to say, so you're not like using the journaling capability of the XT4 here, right? You're using the logging on your own.
Yes, yes, and your voice is slightly low,
Sorry.
but you're talking about journaling, right? So we are, so we do take advantage of the ext4 journal, but we do have our own log as well. Yes.
Okay. So the journaling in the like XT4 is basically to make sure that the metadata operations are guaranteed in terms of the consistency.
So I think it's a little bit more nuanced than that. So um, when you have the user space log, you can provide properties without actually trapping into the kernel, right? So you can use the ext4 journal to do to guarantee metadata operation atomicity, but then you have to trap into the kernel. And what the log provides us is that it allows us to sort of like buffer writes and provide atomicity without going into the kernel. So for certain operations, we have to go into the kernel, but for many operations, we can provide atomicity staying entirely at the user space level.
Okay. Okay. Thanks.
Sure. All right. SplitFS accelerates your data operations by performing them from user space. And it relies on the maturity and the activity in ext4 DAX for metadata operations. It uses user space log and out of place updates for providing logging and synchronous operations. So SplitFS can give you very strong guarantees. Now let's take a look at what is the performance at which you can do this. So we return to our previous operation of appending 4 kilobytes to a file. And you see that here we have SplitFS in its strict mode where all operations are atomic and synchronous. So this is the strongest guarantee that SplitFS can provide. And you see that it takes about 80% overhead versus writing to the device. In other words, the overhead is lower than if you wrote another 4 kilobyte block, right? And the 80% overhead comes from the fact that we are doing so we're doing logging, for example, we're routing traffic and all of these things. And so all of that sort of contributes to overhead. Now, if in the paper, we have actually evaluated SplitFS across a broad range of workloads. And what we notice is that if you have data intensive applications like LevelDB or Redis, for example, then our bet pays off. And we get twice as better performance as Nova for these applications. However, if you have applications where you're mainly metadata operations like git, tar, and rsync, where you're creating lots of tiny files and then you're just basically doing lots of creates and opens and so on. So in this case, we actually have 15% overhead. So if your workload is metadata dominated, then SplitFS is not a good choice, and you will actually have overhead versus using something like Nova. Okay? So SplitFS is open source, and we've done a bunch of work to make it usable by other people. So if you want to use a persistent memory file within your work, please let us know, and we'll be happy to help you. Okay, so now I'm going to slightly transition, and I'm going to talk about how do you build data structures for persistent memory. Matt, did you have a question?
No, okay, sorry.
So how do you build data structures for persistent memory? And the kind of data structures I'm talking about are things like hash tables, B trees, and so on. So we want to build these things. And we want them to have 3 properties. So first, they must be concurrent and give high performance when accessed from multiple cores and threads. But you also want them to be crash consistent. Remember that persistent memory is a durable media. So if you write data to it and crash, it's still going to be there. So when you come back from a crash, you want to be able to recover to a consistent state. We want it to be cache efficient. From looking at data structures designed for DRAM, we know that minimizing cache misses is a central technique for good performance. So we want it to be cache efficient. Now, concurrency is a very hard problem, and crash consistency is another hard problem. When you try to do these things together in one data structure, it is almost inevitable that you have problems. So when we looked at data structures for persistent memory that were handcrafted, designed from scratch, like fast and fair, which is a B tree, and CCH, which is a hash table, we found serious bugs leading to data loss and corruption. And so it sort of raises the question, right? Is there a better way to do this? Should we have to design these things from scratch? And the question we asked ourselves is, can we convert existing DRAM data structures to persistent memory data structures? There's already been decades of research and development into how do you design excellent concurrent data structures for DRAM. Can you take advantage of this in some way? And the insight that we had is that in some DRAM data structures, not all, the mechanisms that they have to get isolation can be used to obtain crash recovery if the data structure is placed on persistent memory. So let me actually explain this with an example. So one way to look at isolation is that you have a read and a write that's concurrently going on. The read should return a correct value irrespective of what the write is doing. You can look at crash recovery in a very similar way. You can say, I have a write and then I have a number of crashes, and then I have a read, and irrespective of these crashes, I want my read to return the correct value. So you can look at crash recovery from the lens of isolation. And we are not the first people to do this. So folks from Michigan had this paper called Memory Persistency in ISCA in 2014, where they have this notion of a crash recovery observer, which sort of uses the same insight. So what we're going to do is we're going to reuse the isolation mechanisms that are there in DRAM data structures for crash recovery. So that's the high level idea. Again, let me use an example. So imagine that you had a lock-free B tree. So for both reads and writes, we are not going to lock our data structure. So what you're looking at is the leaf of the B tree, and so you have sorted list and the empty slot for inserting data. Now, when a writer wants to insert new data, it does so in 2 atomic steps. First, it copies over 2 to the empty slot. Then it changes the second 2 to the new data, which is 3. Okay, so at the end of this, the writer has now inserted new data. However, because we do not use locks, what could happen is that a reading thread may see this intermediate state. So it can look at it and it can see 1, 2, 2, and 5. But if the user asks like for the data in this particular node, the thread will return 1, 2, and 5. So what is happening here is that the reader can detect and tolerate inconsistencies. In this particular case, duplicates. It sees the 2 2s and it can say, oh, it's a duplicate, I'm going to ignore it. Okay? Similarly, let's say the first writer thread crashed after some time, and then another writer thread comes along and it sees 1, 2, 2, and 5. It can notice this duplicate and it can actually fix it. It can say the second 2 is a duplicate, I'm going to erase it. And so we have this empty slot again. So what is going on here is that the writer can detect and fix your duplicate, your inconsistencies, in this case, duplicates. So at a high level, right, this is what you want from a crash consistent data structure. Readers to detect and tolerate inconsistencies so that the user never sees them. You want your writers, if they see inconsistencies, to fix them. It turns out that if you have these properties, you don't need any other crash recovery because the readers are never going to return inconsistent data. Your writers are going to fix your inconsistent data. And this is what we exploit in our work, right? Now, you cannot do this sort of like transformation for every data structure. There are specific kinds of data structures where you can do this transformation in sort of like an easy way. And in our paper, we identify all of these types of data structures. So the first one is actually very simple, and it's just update using CopyOnWrite. So you have a node, you want to insert data, you make a copy of this node, you add the data to the node, then you atomically switch your pointer to the new copy. Okay. Now, if this is how your data structure works, all you really need to do to ensure crash recovery is first you do all the allocation on persistent memory, and then you ensure that the new node that you created is flushed and fenced, and then the atomic pointer switch you're doing is flushed and fenced. And when I say flush and fence, it means that you're pushing it from your volatile CPU caches down to your persistent media. So that's all that means. So it's sort of like summarize, right? For this particular data structure, anything new that you're creating when you're doing copy on write, you have to flush it. And when you do your pointer switch, you have to flush that. You have to make sure they're ordered correctly. And this can be like very few lines of code change in the data structure. Okay? Another type of data structure is what we already saw, right? Where readers can detect and tolerate inconsistencies, and writers can fix inconsistencies. So in this data structure, all you have to do really is that you have to ensure that all your writes are properly flushed and fenced. So for example, if you're when you're doing a write, it's a sequence of like atomic steps. After each step, flush everything, fence, flush everything and fence. Now, we are not claiming that recipe is the most performant way to do this. We are only claiming it's the correct way to do this. So for example, in this particular case, you can use group commit to make sure that you flush everything and then you do a single fence at the end before the commit. There's lots of optimization opportunities that you've not explored. So this is sort of like the baseline that we are setting to. Okay. Similarly, there's another type of data structure where your readers are going to detect and tolerate inconsistencies. Your writers are still going to detect inconsistencies, but they do not fix them, right? So they can only detect them. So in this particular case, you have to use something from the theory literature called a helper mechanism, which basically goes in and fixes your inconsistency. Now, when we tried using this approach on like different data structures, we found that the helper mechanism is usually already part of the code. The code to sort of like zero out this 2 is already part of the code, and you have to call it appropriately. So we call this sort of like general approach recipe, and we've used it to convert 5 different data structures like hash tables, B trees, radix trees, and so on from their DRAM component to their persistent memory component. Okay. And in all cases, the conversion required like less than 200 lines of code. And in some cases, it required like 5 lines of code. But in all cases, if you took the original code base and you did our changes, the resulting sort of like, like patch or your pull request is small enough that somebody could read it and understand what it is that we're doing. And sort of convince themselves that, this is a reasonable thing to do. In sort of like the worst case code that we changed, it was about 9% of the code. But again, like, like more than the lines of code, it's knowing what to change that is the challenge. So we're not claiming that recipe is an automatic way, right? You have to understand the underlying DRAM data structure. But if you do understand it, what we can provide is a way to do the conversion such that you can eyeball all of the changes you're making and sort of like convince yourself you're doing something reasonable. So it's sort of like a straightforward way to do that. Now, when we compare the performance of our data structures with sort of like handcrafted data structures, like designed from scratch, like Fast and Fair and CCH, we saw significant performance gains, up to 5x in multi-thread evaluation. And the reason for this is that like we are able to preserve the good properties of the DRAM data structures we convert. The DRAM data structures we selected were all like top of the line, like excellent performance, and we're able to retain the good performance of those data structures. Our data structures have very low cache misses compared to sort of like the things we evaluate against, and that really is sort of like the root cause of the good performance. So recipe is open source. So we have like 5 different data structures that we have converted. We call it the P family of data structures. So there's hash table, B tree, and so whatnot. So if you want to use data structures in your sort of like research, please let us know, and we'll be very happy to sort of like help you to do that. So now I want to talk about sort of like the big theme that connects SplitFS and recipe, which is that we want to use existing software artifacts to solve new problems, right? So in the case of like SplitFS, we were taking advantage of the fact that ext4 exists, it's widely used, there's lots of activity, people are like working on it every day. In the case of recipe, we want to take advantage of the fact that these excellent DRAM data structures already exist, they've been widely used, bugs have been worked out, and so on. Right? Now, if you take advantage of these existing artifacts and you sort of like build on top of them in like surgical ways, it really helps adoption, because you can say, I took this sort of like very well-known data structure and it made these sort of small changes which you can read like on a single screen, and then you get a new data structure. And people are much more likely to believe you and adopt your data structure versus if we say, I built like 7,000 lines of extremely new code. So it sort of like helps adoption quite a bit. And doing this requires a lot of thought, though. So you want to be sure that the changes that you're making are correct, and that is very challenging. But it's very satisfying when you can pull this off.
Which hash table like did you use here? Which hash table?
So I think we used. I'm not sure off the top of my head actually. So I think it's. I mean, I don't remember the name, but these are hash tables. This is a family of hash tables designed by people who from I think. Man, I'm so blanking out on the name, but it is designed to be store optimal hash tables. So the original reference is from Atlas, and so I after the talk I can sort of like give you the reference for that.
Okay.
So but the hash table itself is sort of like designed to be as few cache misses as possible. I think it's called cache line optimized hash table. I think that's the full name. Yeah.
Okay. I was asking because like the most of the state of the art ones are like they do one big allocation like the cuckoo hash table, and the pointer swing is not really like easy to do in those kind of hash tables, and they perform very good. But maybe like in this one, like I can check offline about that.
Yeah. No, I mean, yeah, we can definitely follow up offline. Yeah.
Cool. Thanks.
Yeah. All right. Okay. So now I'm going to talk about new applications for storage system and sort of like the stresses they put on storage systems. So there's been a number of new applications, right? And since mine is a storage lab, what we do is like for every sort of like new domain that comes along, we ask, does storage matter for this domain? And what we've always found so far is that yes, it does matter, and it matters significantly, and we can use that to sort of like build better systems. So we worked on storage for machine learning, and I'm going to talk about one of our projects today. We have worked on storage for blockchains, and we have worked on storage for privacy regulations such as GDPR and CCPA, and how do you build compliance systems for that? And I'm happy to talk about any of these things sort of like offline. So now I'm going to talk about our machine learning work. And this is a collaboration with Microsoft Research. And what we're going to do is we're going to look at the training time for machine learning models. And we're going to look at very specific type of machine learning models. We're going to look at a deep neural nets. We're going to look at data intensive deep neural nets. So think about like computer vision, audio models, multimedia models, which require terabytes of data, right? So this is not, what I'm going to talk about is does not apply to like NLP, where your data set is small and can be cached in memory, right? So this is what the training pipeline usually looks like. So we have your data on an SSD, and you usually compress to save space. The compression factor is about like 5 to 7 times. You're going to read your data into sort of like memory, and you have like a DRAM cache. You're going to decompress data from your cache, and you're going to apply random transformations. So for computer vision, this is going to be things like rotating your image, perturbing your image, cropping your image, and so on, right? And the random transformations are important because that is what really allows your model to learn. You want to do them sort of like in the critical path, like on the fly, right? Once you're done all of this, then you feed it to your GPUs, and your GPUs are the most expensive resource in your entire hardware setup, right? So you want to ensure that your GPUs are not idle. So let's look at this whole pipeline from a data perspective and the speed at which we can do things, right? So in what I'm going to tell you, we are going to be doing prefetching all we can from storage. We're going to use every thread available to do parallelism. So it's all with prefetching and parallelism, okay? So if you have a good SSD, you can read data from your SSD at about like 500 MB per second. Since you have a DRAM cache, your effective throughput with hits is going to be about 800 MB per second. You're going to be able to decompress at about 1300 MB per second, and then apply random transformations at about. However, your GPUs, if you have like 8100 GPUs, requires about 2200 MB per second, right? So in this particular setup, your GPUs are going to be idle, waiting for data to be processed and sort of like sent over to them, right? So we call this general concept data stalls, very similar to sort of like the compute architecture concept where you're basically stalled waiting for data. And you can sort of differentiate data stalls into two kinds. So one of them is called preparation stalls, where you're preparing the data using your CPUs, you're doing all these random transformations, and you're not able to do them fast enough for your GPUs, right? Another kind of stall is called a fetch stall, where you're fetching your data from storage into DRAM, and you're not able to do that fast enough. So in this particular example, the data is stored on like very slow magnetic hard drives, so you get low random access throughput, and so that is going to be the main stall for the entire entire pipeline. So what this sort of like shows us is that for a given sort of like model and for a given hardware setup, you need balance among your different resources to make sure that your GPUs are not idle, right? So if you have a certain number of GPUs, they're going to require data at a certain rate, which means you need a certain number of vCPUs to process your data. If you have a certain number of vCPUs, you need a certain storage bandwidth to keep your vCPUs happy, right? So these have to be sort of like in proportion to each other. And what we notice is that if you look at ML optimized servers in like Amazon and Google and so on, they are not really optimized, right? So you have servers where, for example, they have like lots of GPUs, but then very little compute, because then you will not be able to process your data fast enough. You have servers with like lots of GPUs, but very little storage, or storage across like a very slow remote network. So you're not going to be able to get your data fast enough to your machine to sort of like process it. So this sort of like gives rise to interesting insights like this, and also tells us if you want to rent, like an instance on like Amazon or whatever, what the best strategy can be, right? So in this particular example, you are not saturating your GPUs. You're only able to sort of like feed 1/3 of your GPUs with the pipeline that you have. It does not make sense to rent an 8 GPU machine and have your GPUs idle, right? The cost is usually dominated by the number of GPUs you have. You might as well get a machine with, let's say, 4 GPUs and then use that to sort of like, higher capacity. So this sort of like tells us like, what kind of hardware setup you should buy. And we built this tool called DS Analyzer for this. So what you do is you take your PyTorch or TensorFlow training script and you sort of like give it to DS Analyzer, and it'll actually train your model a few iterations. It'll measure a whole bunch of things, such as like how much memory is used, at what rate you can feed your GPUs, all of these things. And then it can answer questions for you. So you can answer questions like, what happens if my storage bandwidth becomes double? Will my training throughput increase? What happens if I double the number of GPUs I have? Will my overall training throughput increase? If I moved on to a different server with double the number of vCPUs, will my training throughput increase? So it can answer all of these questions for you. And we're really targeting DS Analyzer for like data scientists, right? So folks inside like Amazon and Google, they can figure this out and they know this. But if you're someone who's trying to train a model and renting an instance on Amazon to do it, DS Analyzer can help you figure out what is the best way to do that, right? To get the most bang for your buck. So another thing we looked at was, let's say you're stuck with a particular hardware setup. Now what can you do, right? It turns out you can still do much. So we built Cordial, which is a new data loading library. And at a high level, what it does is it reduces data stalls. So let me explain it with an example. So let's say you're doing hyperparameter search on a single server. So you have 8 instances of the job. And what we're doing is we're running each of them with like different parameters. And we are basically seeing which one performs best. We'll be killing ones that don't perform well and instantiating them freshly. The key point here is that they're all doing the same work. So if you look at 8 hyperparameter instances on a single machine, they will read data 8 times and they will pre-process the data 8 times. And you don't need to do this, right? I mean, it's like redundant work. And so that is what Cordial will do. So it understands ML semantics. So it understands, for example, that within an epoch, you want to see every data item exactly once. You don't want to see it twice, all of those things. And it will eliminate all the redundant work so that, for example, if you have 8 hyperparameter jobs, your data is only read and pre-processed exactly once, not 8 times, right? So it cuts down on a lot of the work. And the really nice thing about Cordial is that you can get impressive gains. Like, for example, for hyperparameter search, you can get about 5 times better training throughput without changing the model and without changing TensorFlow or PyTorch. Complete box with respect to those aspects. All it's really doing is changing how you fetch and process data, right? So that's all it's doing. And if you're using a distributed cluster to this, what Cordial will do is, if the data that you want is in the memory of another machine, you go ahead and fetch it from there rather than fetching it from slow storage and processing it on your own local node. And this also results in significant gains, right? So overall, the idea is that we want to be cognizant of data stalls, and what our Cordial library will do is it will help you eliminate redundant work and reduce data stalls, right? So with that, I sort of like briefly want to talk about like 2 other work. This is not in detail, this is like a 1-minute flyby presentation, but I think it can help some of the students listening to the talk. So one of the work that we did is called PebblesDB, and it's a write optimized tool. So if you use a key value store like RocksDB, for example, it has something called a log structured merge tree as its underlying data structure. And at a 10,000 feet level, what RocksDB will do is it will rewrite the data again and again to ensure it is sorted. So every time you want to read some data, you do a binary search and you get your data. So it's very quick, but it rewrites your data quite a bit. So in PebblesDB, the very high level idea is let's not keep your data entirely sorted, let's keep it partially sorted. So we combine skip lists and log structured merge trees to do this. And the idea is that you get a balance between your read performance and your write performance. So PebblesDB can reduce the amount of traffic you're writing by like 50% while maintaining the same performance. And it's open source. So if you want to use it, we're very happy to help you do that. Another thing which could be helpful to students is this tool we built called CrashMonkey. So it is a tool to test whether your file systems recover correctly after a crash. So this is one of the essential aspects of a file system, and you want to make sure it does it correctly. But CrashMonkey is a tool that can help you do that. And it's file system agnostic. So we don't care about the internals of your file system. As long as it's implementing the POSIX interface, we can do it. Sort of like a nice story here is that we built CrashMonkey and it got accepted to OSDI, and we were giving this practice talk. And somebody in the audience said, "Hey, did you run it on a verified file system?" And we were like, "We didn't," but like that weekend, my grad student went and ran it on a verified file system and actually found a bug. And if you're confused how a verified file system can have a bug, there's a verified core, and then it talks to an unverified library to actually do I/O. And the bug was in that transition. So it speaks to the sort of like the ease of use and the power of CrashMonkey that we could take a file system we didn't know anything about and find a bug over a weekend. So if you're developing file systems at Berkeley, like we would love to help you test them with CrashMonkey. So now I'm going to talk a little bit about future challenges that I see in the realm of storage, and what challenges I see there. So one challenge is that the line between memory and storage is blurry, right? So if you are working with magnetic hard drives, for example, you could be very inefficient in terms of like memory or CPU, and your hardware access is going to take like milliseconds, so it heat all of that. But as your storage becomes faster and faster, you no longer have this effect. And with persistent memory, right, every read or write is about 100 to 200 nanoseconds. So this means that even a page fault matters. So if you have a 2 megabyte file and you're memory mapping and reading this file, the number of page faults you take while you're reading this file are important for performance. So if you have a huge page and you took one page fault, that is vastly faster than if you took a number of page faults where like you have 4 kilobyte pages. So page faults matter quite a bit. And this is an interesting problem because it turns out in sort of like our traditional file systems, it is very, very easy for the file system to get fragmented, right? Your data is sort of like all over the place. If you imagine file systems like log structured file systems, sort of like by design, they're writing data all over the place. Same for copy on write file systems. They don't get huge pages at all, which means the performance goes down quite a bit. So one challenge here is like, like how do we do this? How do we make sure that our huge pages are not fragile? And this, I think, requires both an architectural solution and a system solution, because there's only so much we can do given the page tables that we have. Another thing that we are working on is these new privacy regulations like GDPR and CCPA, and how do we build systems that are compliant to them. So in communication of the ACM, in February's issue, we have an article called GDPR anti-patterns, where we talk about, where we basically translate your legal GDPR requirements into sort of technical constraints, into design constraints, basically. And we show you how it's sort of like against a lot of the things we've been doing so far. So for example, one of the things we do is like we collect data from the user and around forever, right? So this is illegal under GDPR. Every piece of data that's collected must have a specific purpose associated with it and a specific time to live. So it must be deleted after a certain amount of time. So our sort of like papers and sort of like articles on the topic will help you sort of like see things like these and sort of like show you how building a GDPR compliant system is sort of like challenging. Another thing that we're working on is how do we verify existing storage systems written in C. So a lot of the verification work is on building or synthesizing new storage systems out of specifications. So you have like a high level specification and you synthesize like a correct file system from that. And folks in like MIT and Washington are working on this. But we also want to do something for the existing C-based file systems like ext4, BetterFS, and so on, which are very widely used, but are not very amenable to verification because we have void pointers everywhere. Like very, very hard to do these things, right? So we're working with PL folks at Austin, like James Bonholt and Michel Dillig, on how do we do sort of like piecewise verification of C-based systems. Finally, how do we build disaggregated storage systems, right? Specifically, we are looking at disaggregated persistent memory. And this is a challenge because like the latency for persistent memory is about 100 nanoseconds. But if you want to access it over the network adds up at least like 1 to 5 microseconds. So how do you build data structures for persistent memory? How do you build storage systems for persistent memory? Disaggregated persistent memory is something that we are looking at. So in conclusion, it is a very exciting time to be a storage researcher. Storage has always had challenges, but now is sort of like a special time in that there are new storage devices coming out. There are new applications which are like using storage in weird ways. And it's very challenging to optimize these systems. My plea to the grad students hearing this talk is that we can use existing software artifacts like the ext4 file system, existing data structures to solve new challenges, right? For persistent memory, for example. And if you do this, it's very exciting. It's very challenging to do this correctly, and it aids adoption. So when you do this and you go to a user, they are much more likely to adopt your system. And in a lot of the work that I talked about during this talk, we actually had to collaborate with theory folks. For example, for PagodsDB, for Recipe, and so on. And if you find the right theory collaborator, right, it is amazing. It's like they will pull out amazing results out of their hat. So it's beautiful working with them. And as we have like harder and harder challenges, we will require interdisciplinary collaboration. So my plea for grad students is like, try and collaborate with theory folks. And with that, I'd be happy to take questions. Thank you.
Thank you very much, Vijay. Do we have any questions?
So I was interested in the stuff you did on finding the right balance of resources for, say, these ML pipelines. How do you think that scalable cloud storage systems fit into that? Basically, this ability to transparently and dynamically scale the storage, say, bandwidth available to you just on demand. So you didn't allocate anything, right? Like S3, the more you read from S3, the more bandwidth you get, right?
Yes.
How do you think that impacts
Yeah, so in our paper, we actually do have evaluations with S3. So we show that, so in sort of like most of our analysis, like what S3 ends up becoming is the sort of like longer latency, higher bandwidth device instead of the SSD that you have, right? Now, in many cases, depending upon the objects that you're storing in S3 and the sizes and so on, it is possible to get like poor performance even on S3. But ideally, what you're saying is what we want, right? We want basically a disaggregated system. We want a system where we want to do this sort of like machine learning training. And if you want more compute, it gives us more compute. If you want more storage bandwidth, it gives us more storage bandwidth. How we build such a system is sort of like the challenge. But like you're right in that if we had a system like that, it would totally solve that problem.
Does that answer your question?
Yep.
Okay, great. Are there any more questions?
I was curious at what people thought about your work on the GDPR, and specifically, when you talked about it with lawyers, for instance.
Oh yeah, that was always very interesting. So we collaborated with the law school at UT to do this, and what we would basically do is we would meet with them and we would be like, here are the laws that you're interested in. Then we would have our interpretation of this, right? So we would think that, like when the law says something, we have a certain interpretation. Do you think this is correct? And then we will discuss that with them. And they would sometimes say that, like, no, you can't really assume this from this law. And sometimes you'll be like, yes. But one of the things that we noticed was that law documents by design are very, very vague. So for example, when you have this sort of like time to live, right? Every piece of data that's collected must, after a certain amount of time, be deleted. The law does not tell you it must be deleted in like one day. What the law tells you is that it must be deleted in a reasonable amount of time. What Google is arguing is a reasonable amount of time for them is 180 days, right? So we are in very new territory here because the judges don't know anything, right? And they can't be like, oh, 180 days from Google, okay, that seems reasonable. Like let's pass that. Whereas like if we could show using technological solutions that no, you can actually do this deletion very, very quickly, then we can convince the courts to say that like what is the reasonable amount of time is actually like 2 days. And Google or Facebook or whatever must delete the data in 2 days, and then we move the law forward. So there's quite a bit of like space for impact in this sort of like work. But the problem is that it's very interdisciplinary. So when you go and talk about it to systems folks, for example, they are not always sure it is systems, right? And one of the nice things we liked about the database community is that it is broader than sort of like systems, and they were quite welcoming of this work. Whereas like when we send this to systems people, they're like, it is very nice, but it's not systems. And so, yeah.
So I've got a question. So to follow up on that, so are you like filing amicus briefs or something with on these like court decisions on? Oh, okay.
No, we are at a very, very early stage in this, I think. So there's, I think, 3 groups working on this currently. So one is like, so my postdoc Supreet over here, he's now faculty at Iowa. He's the one sort of like led this work while he was at my lab. So he's continuing to do this work. We also have Malte at Brown, who's continuing to do this work. So, and then my group. So we have 3 groups sort of like pushing on this. But right now, all of us are trying to explore the technological side of things. So for example, if you have like a trillion sized database, right? And you want to delete a key, what is the absolute fastest way to do this, right? And can you prove that you can do this even if you have like, lots and lots of data? So we are focused on things like that. Getting to the point where we can sort of like push Google and say, you have to delete your data in 2 days, I think is like quite a bit down the road, but we hope to get there.
Okay,
Actually,
very interesting.
There is a group at Boston, BU. They had a paper last year around this, like it's called like Alethi, where they had guarantees on the deletion in LSM tree.
Very interesting. I don't think I was aware of this work. I'll look it up.
It's called LETHE. It was in SIGMOD last year in 2020.
Okay, SIGMOD last year. Okay, I'll go look it up. Yeah.
Cool. Well, we're coming up on the hour. Are there any further last minute questions? I guess not. Well, let's all thank Vijay again for coming and for giving us his very interesting talk. And yeah, Vijay, if anyone has any follow-up questions, should they feel free to email you? I don't know if I'm pushed.
Yeah. No. I mean, like, So I mean, first, like, it was a pleasure. Thank you for hosting me, and feel free to sort of like, send me an email about any of this work. I'm really happy to chat about it.
Excellent. Well, thank you very much.
Thank you,
And
folks.
everyone have a good weekend.
Yeah.